Learning regret minimization and equilibria. Many situations involve repeatedly making decisions in an uncertain environment. For instance, deciding what route to drive to work each day, or repeated play of a game against an opponent with an unknown strategy. In this chapter, we described learning algorithms with strong guarantees for settings of this type, along with the connections to game theoretical equilibria when all players in the system are simultaneously adapting in such a manner. We begin by presenting algorithms for repeated play of a matrix game with the guarantee that against any opponent they will perform nearly as well as the best fixed action in hindsight, also called the problem of combining expert advice or minimizing external regret. In a zero-sum game, such algorithms are guaranteed to approach or exceed the minimax value of the game and even provide a simple proof of the minimax theorem. We then turn to algorithms that minimize an even stronger form of regret known as internal or swap regret. We present a general reduction showing how to convert any algorithm for minimizing external regret to one that minimizes this stronger form of regret as well. Internal regret is important because when all players in a game minimize this stronger type of regret, the empirical distribution of play is known to converge to correlated equilibrium. The third part of this chapter explains a different reduction, how to convert from the full information setting in which the action chosen by the opponent is revealed after each time step to the partial information bandit setting, where at each time step only the payoff of the selected action is observed, such as in routing, and still maintain a small external regret. Finally, we end by discussing routing games in the wardrobe model, where one can show that if all participants minimize their own external regret, then overall traffic is guaranteed to converge to an approximate Nash equilibrium. This further motivates price of anarchy results. Introduction. In this chapter, we consider the problem of repeatedly making decisions in an uncertain environment. The basic setting is we have a space of n actions, such as what route to use to drive to work, or the roles of a matrix game like rock, paper, scissors. At each time step, the algorithm probabilistically chooses an action, say selecting what route to take. The environment makes its move, setting the road congestions on that day, and the algorithm then incurs the loss for its action chosen, how long its route took. The process then repeats. The next day, what we would like are adaptive algorithms that can perform well in such settings, as well as to understand the dynamics of the system when there are multiple players, all adjusting their behavior in such a way. A key technique for analyzing problems of this sort is known as regret analysis. The motivation behind regret analysis can be viewed as the following. We designed a sophisticated online algorithm that deals with the various issues of uncertainty and decision-making, and sell it to a client. Our algorithm runs for some time and incurs a certain loss. We would like to avoid the embarrassment that our client will come back to us and claim that in a retrospect we could have incurred a much lower loss if we used his simple alternative policy pi. The regret of our online algorithm is the difference between the loss of our algorithm and the loss using pi. Different notions of a regret quantify differently what is considered to be a simple alternative policy. External regret, also called the problem of combining expert device, compares performance to the best single action in retrospect. This implies that the simple alternative policy performs the same action in all time steps, which indeed is quite simple. Nonetheless, external regret provides a general methodology for developing online algorithms whose performance matches that of an optimal static offline algorithm by modeling the possible static solutions as different actions. In the context of machine learning, algorithms with good external regret bounds can be powerful tools for achieving performance comparable to the optimal prediction rule from some large class of hypotheses. In section 4.3, we described several algorithms with a particularly strong external regret bounds. We started with the very weak greedy algorithm and built up to an algorithm whose loss is at most big O of square root of t times log n greater than that of the best action, where t is the number of time steps. That is, the regret per time step drops as big O of square root of log n over t. In section 4.4, we show that in a zero-sum game, such algorithms are guaranteed to approach or exceed the value of the game and even yield a simple proof of the minimax theorem. A second category of alternative policies are those that consider the online sequence of actions and suggest a simple modification to it, such as every time you bought IBM, you should have bought Microsoft instead. While one can study very general classes of multiplication rules, the most common form, known as internal or swap regret, allows one to modify the online action sequence by changing every occurrence of a given action I by an alternative action J. The distinction between the internal and the swap regret is that internal regret allows only one action to be placed by another, whereas swap regret allows any mapping from 1 to 3 until n to 1 to 3 until n, and it can be up to a factor n larger. In section 4.5, we present a simple way to efficiently convert any external regret minimizing algorithm into one that minimizes swap regret with only a factor n increase in the regret form. Using the results for external regret, these achieves a swap regret bound of big O of square root of t times n log n. Algorithms for swap regret also have been developed from first principles. See the notes section of this chapter for references. But this procedure gives the best bounds known as for efficient algorithms. The importance of a swap regret is due to its tight connection to correlated equilibria, defined in Chapter 1. In fact, one way to think of a correlated equilibrium is that it is a distribution Q over the joint action space such that every player would have zero internal or swap regret when playing it. As we point out in section 4.4, if each player can achieve swap regret epsilon times t, then the empirical distribution of the joint actions of the players will be an epsilon correlated equilibrium. We also described how external regret results can be extended to the partial information model also called the multi-armed bandit MAB problem. In this model, the online algorithm only gets to observe the loss of the action actually selected, and it does not see the losses of the actions not chosen. For example, in the case of driving to work, you may only observe the travel time on the route you actually drive, and do not get to find out how long it would have taken had you chosen some alternative route. In section 4.6, we present a general reduction showing how to convert an algorithm with low external regret in the full information model to one for the partial information model, though the bounds produced are not the best known bounds for this problem. Notice that the route choosing problem can be viewed as a general sum game. Your travel time depends on the choices of the other drivers as well. In section 4.7, we discuss results showing that in the wardrobe model of infinitesimal agents considered in chapter 18, if each driver acts to minimize external regret, then traffic flow over time can be shown to approach an approximate Nash equilibrium. This serves to further motivate price of anarchy results in this context, since it means they apply to the case that participants are using well-motivated, self-interested adaptive behavior. We remark that the results we present in this chapter are not always the strongest known, and the interested reader is referred to the recent book Cisa Bianchi and Lugosi 2006 that gives a thorough coverage of many of the topics in this chapter. See also the notes section for further references.